Okay, so in this lesson, we're going to just focus on the idea of trying to take two simple graphs, two simple functions, combining them by adding them together, and then showing what the resulting function or resulting graph would look like. My suggestion for this activity was to actually try to do this handout on your own first, and then use the video to help you out to check your answer or if you get stuck or anything like that. So let's look at the first one. So we have two graphs. I've just started this time with the two graphs. F of x, which on my screen is blue, and g of x, which is in red, and we're going to add them together. Now, in some ways, you don't need to make this any more complicated than it is. Like, let's look at this point right here where they intersect. Both y values look like they're about 1.5. So when you add functions, you're just adding their y values together. Okay, we're adding f of x plus g of x. So that's about 1.5. So if you add 1.5 to 1.5, then you get 3. So there's going to be a point about right there. Okay. Same with if I go down, anywhere else in the graph, that's going to be true. Like right here, that's just a little bit bigger than 0. Plus 6 is just a little bit bigger than 6. So there's another point right there. If I look here, I've got a number 1, it looks like, plus, say, 5. We're going to be at 6. So this portion of the graph is just going to look like this. Okay. Down here, for this side of the graph here, we've got small blue values, okay, plus, larger, more significant red values. Now notice, like, if I look at a number, say right here, this is -4, and a number looks like it might be -1/10 or -1/3 or something, is going to give you a point, which is right about there. So we're below the red line here. Since we're adding a negative to another negative, that gets an even bigger negative, or smaller negative, I guess is the correct word. This part of the graph is just going to look like this right here. Something like that right there. And this should be if you've done the other lesson, this is there's an example very, very similar. In fact, it's exactly the same. So moving down. Now, if you're wondering about where these graphs came from, well, the first graph, f of x, is just 1 over x. And the second graph, g of x, was x plus 1. I just put those in Desmos. So that means that the graph that I've added, the black curve here, is actually the graph of f of x plus g of x, or 1 over x plus x plus 1. Now I can combine those or simplify that expression by coming up with a common denominator. The common denominator, of course, just being x. Just like that. And so then I've got a common denominator, so I can write it all out of x. And here you get x squared plus x plus 1. For our simplified equation. And that, of course, we called h of x. Oops. So h of x, the black graph, is really this graph, this equation right here, x squared plus x plus 1 divided by x. So it's not a big surprise that it still has a vertical asymptote at x equals 0. Now, most of the time, if you did the other lesson first, we actually took this equation and used division, okay, to get the equation 1 over x plus 1. Now I'm just looking at it sort of backwards and saying, imagine starting with f of x of g of x, creating a new equation by adding them together, and then getting the graph of that by just adding their y values on the graph. So in the next question, we ask ourselves, notice that h of x doesn't have any intercepts. It doesn't cross the x or the y axis. So now that we have the equation for h of x, does the equation tell us the same thing? And of course it does. I mean, equations always tell the same story that the graph does. So if we start with the idea of the y-intercept, the y-intercept would be when x is equal to 0. But if we look at the equation, there's an x in the denominator, so that can't be 0. So x can't be 0. And we could say that there's no y-intercept. Moving on to the x-intercept. At the x-intercept, h of x is equal to 0, or x squared plus x plus 1 would have to be 0. The only way to make a fraction 0 is to make its numerator 0. So at our x-intercept, if we went to solve for that, we'd be looking for solutions to 0 equals x squared plus x plus 1. And we find that no solutions exist. It doesn't factor, but more importantly, if you put that in the quadratic formula, you would find that b squared minus 4ac, the stuff that's under the square root sign, is less than 0, and so you have a negative sign under the square root. So this just has no solutions. I'll leave that for you to check if you want. So yes, algebraically, we can see there's no intercepts. And then what are the asymptotes for h of x? Well, there's a vertical asymptote at x equals 0. And our justification algebraically for that is there is a x in the denominator, okay? It doesn't divide out, so therefore it has to be a vertical asymptote. And we also have an oblique asymptote. Now the oblique asymptote ends up being the equation y equals x plus 1, which is actually the red diagonal line in the picture here. Now we can verify that algebraically by looking at, so oblique asymptote, y equals x plus 1. We can verify that algebraically just by looking at the equation, and when it's written in this form right here, you can see that as x gets really, really big, 1 over x becomes insignificant, and the graph gets closer and closer to x plus 1. So that's sort of your algebraic verification for why that's true. So nothing you really need to show there other than I just sort of talked about that out loud. Okay, let's move to example 2. So again, we've got two graphs, and we're going to come up with the sum of the two graphs. And this is another example that we've kind of seen before in the previous lesson if you did it first. So red and black, we're going to add those together and we're going to sketch it in blue. So again, just like the other example, don't be afraid to just take a few points and add them up. I mean, if we're adding f of x plus g of x, then we're talking about adding their y values on the graph. So for example, they both have a y value of 1 here, which means that h of x, the sum of the functions, would have a y value of 2. And then same with over here. This is going to have to be 2. You can do a few more points if you want. Here's one at 3, and that one looks like it's about a half or about a third maybe, which means there's another point right here. Okay, there's another y value of 3, and that one looks like it is also about a half, so there's another point right here. So if we started adding the red graph to the black, we're going to be above the red graph here. Okay, because we're adding the red values to some y values that are getting smaller and smaller and smaller. So we get this part of the graph looks like this. And then again, now the black part takes over and the red becomes smaller. So we end up being above the black like this. Move to the other part of the graph, and it's basically the exact same picture. We end up getting the exact same thing. And there you go. That's h of x graphed in blue, which is f of x plus g of x. Okay, in the graph above, f of x is x squared and g of x is 1 over x squared. So find a simplified equation for the graph that we just graphed. So in this lesson, again, we're starting with the graphs and we're coming up with the equations of them afterwards. We've actually done this example already too. So this is really x squared plus 1 over x squared. Okay, f of x, x squared, g of x, 1 over x squared. Find a common denominator. So the common denominator is x squared. Multiply that by x squared, you get x to the power of 4 plus 1 divided by x squared. So that's the equation for h of x. X to the power of 4 plus 1 all divided by x squared. And we can think of that as the sum of y equals x squared, the red graph, plus 1 over x squared, which is the black graph. Can the asymptotes of h of x be verified algebraically? Sure. It's easy to see that the vertical asymptote is at x equals 0 because it's in the denominator of the fraction here. Now, the parabolic asymptote is a little harder to see, but I'm going to talk about it right here again using when the equation's written in this form right here. Okay, as x gets really, really big, 1 over x squared becomes very, very small, and x squared is more significant. So what ends up happening is x gets bigger and bigger. This fraction on the right becomes so small, the graph starts to look more and more like x squared. So that's like a parabol. Sometimes called a parabolic asymptote. And we saw that in the last lesson. So our justification algebraically is just looking at the equation when it's written as a sum like that. Okay, in example 3 here, finally a new looking graph, or what's going to be a new graph. We have the black graph, which has 2 pieces, and the red graph, which has 2 pieces as well. Now, you'll notice that the black graph sure appears to have an asymptote at x equals 4, a vertical asymptote, and it does. And the red graph has one at x equals -3 right there. For now, let's just talk about creating the sum of f of x plus g of x and what that would look like. So here we're adding some positive red to some negative black. It's hard to tell whether the positive is bigger than the negative, but it looks like it is. So one would expect that we are slightly above the x-axis here. Let's try that again. Something like this. Now, the black graph kind of stays close to 0, but the red graph starts to take off. So this is really going to start to do this right here. Okay. Okay. Then we're going to jump over here. And now notice in this part of the graph, the red is really big negative and the black is just small negative. So the graph's going to kind of be just below the red graph here. Like that. Now, what eventually ends up happening is the black graph, which was small, all of a sudden in here starts to become significant values, and the red one becomes less and less significant. So you have like, I mean, let's just imagine adding one here. Here's -1, here's negative a little bit. So there's a point down here. Okay, and then down in here we've got big values, big negative values, like -5, compared to small ones. So there'd be another point right in here. So this graph basically just does this right here. You can almost join those two sections together. Okay, and then we hop over here and we see we have the black graph, which has big values and small negative red values. So the rest of this graph is going to look something like this right here. Okay. Now, none of this is exact. I don't know for sure that this blue graph part here doesn't dip below the x-axis, and I don't know for sure that it does here, but it gives me the general shape. In general, when you add the red and the black graphs here, the general idea is you do get something like this, a section right here, a section right here, and a section right here. Okay, so that's the basic shape we get from adding those graphs together. So in the next part here, I've actually given you the equations. So f of x was actually 1 over x minus 4, and g of x was -1 divided by x plus 2. Those are actually pretty simple graphs, and it shouldn't be surprising that that's what we got. I mean, the black graph, 1 over x minus 4, although I didn't draw the asymptote at x equals -4, it's right there, or x equals +4, it's right there. And it's just like 1 over x that's been shifted to the right by 4. And g of x was -1 over x plus 2. So that's a lot like 1 over x that's been shifted to the left too, but also been reflected. So instead of going like this direction, it instead is reflected like that. So, and there it is right there, the red graph right there. We added them together and we get 1 over x minus 4 plus -1 over x plus 2, or I've just written -1 over x plus 2. So we can actually simplify that. It simplifies to x plus 2 subtract x minus 4 all divided by x minus 4 times x plus 2. Just like that, which equals, sorry, this is a bit of a mess here, 6 divided by x minus 4 times x plus 2. So there it is. There's h of x right there. That's our equation. Now, there are asymptotes on h of x. You should clearly see from this equation right here that there are asymptotes at x equals 4 and x equals -2. And they're the same asymptotes you had from these two graphs here. So when you add two graphs together, add two equations together, any asymptotes those equations have are going to show up in your final graph as well, in your final equation. Now, there's also a horizontal asymptote at y equals 0. You can see that if you look at the blue graph right here and right here. And you can actually see it algebraically too. Remember, the degree of the denominator is greater than the degree of the numerator. And so you end up getting a graph that approaches 0. So y equals 0 for a horizontal asymptote, and your two vertical asymptotes at x equals 4 and x equals -2 is what we end up with. So 3 asymptotes. Okay, next example. So again, we've got h of x and g of x. Again, g of x in red and f of x in black, and we're going to try adding them together. So if we look over here, we've got some small negative numbers, kind of like -1/3. So, I mean, if we add two negatives, we might end up with a point. But slowly the red values get bigger and bigger. So in here, for example, you're adding -3 to about 1/2. So you're going to end up with something like -3.5 down here. Okay, just remember, you're just adding these values together. This portion of the graph is just going to kind of follow the red graph, but be a little bit lower because the black graph sort of shifts it down. Now, it sure looks like x equals -2 is a vertical asymptote, and it is, okay? So we move to the right of that, and we've got, now all of a sudden, we've got big positive red values plus some negative black. So if you add a big positive, like say, well, 4 is not that big, but add 4 to say -1/2, you're going to end up with a point here at about 3.5, so right there. So all these points end up being underneath the red graph. And then somewhere something happens because the black all of a sudden starts to get very big. I mean, here even we have -1 plus 1/2 is -1/2, so that's actually a point right there. And eventually the graph starts to follow the black graph as it becomes more and more significant. So something like this ends up happening. And in this part right here, I'm taking numbers like -2 and adding a little bit to it. So maybe it should be a little lower, but you get an idea of the shape here, that this starts to become the dominant y values, and you're just adding some positives there. This one, again, looks like it has a vertical asymptote at x equals 2. And so on the right side, now you've got big black adding small reds here. You end up getting this right here. And the blue graph is what you would get if you added all the y values in f of x to all the y values in g of x. Well, how did I make the black and the red graphs? Well, the black one, f of x, was just 2 divided by x minus 2. And the red one was 1 divided by x plus 2. So remember, those graphs are also very similar to 1 over x. This one's been shifted to the left by -2. Sorry, it's shifted to the left 2. This one's been shifted to the right 2, and there's been a vertical stretch of factor 2 as well, because you multiply 1 over x by 2. So these graphs that we're adding in these last two examples are really just very similar to the graph of 1 over x, with just a couple transformations done. So if h of x is f of x plus g of x, let's look at its equation next. We get 2 over x minus 2 plus 1 over x plus 2, which simplifies to 2 times x plus 2 plus 1 times x minus 2 all over x minus 2x plus 2. If I then just simplify the numerator there, I will get 2x plus 1x is 3x, and 4 plus -2 is 2. 3x divided by 2 all over x minus 2x plus 2. I'm not going to expand the denominator. It's actually nicer to have that factored. So there's h of x. So we know the graph of 3x plus 2 over x minus 2x plus 2 ends up being this blue curve we have here. And we did that by starting with some simple graphs and adding them together. So, I mean, this doesn't tell you how does one go about graphing something like this. Well, the nice thing to do is actually to take this equation and actually break it up into these two equations here. But we don't know how to do that yet. We'll learn that later on. Now, as for the asymptotes, I can definitely see that there will be vertical asymptotes at x equals 2 and x equals -2 because of the denominator here. Okay, so vertical asymptotes at x equals 2 and x equals -2. And then other asymptotes happen because of end behavior. So what happens as x gets really, really big? Well, notice that this is degree 1 and this is degree 2. And we talked about this quite a bit already. If the denominator has a bigger degree than the numerator, then the graph is going to get closer and closer to 0. So this also has a horizontal asymptote, or I'm just going to say HA for short, at y equals 0. And sure enough, in our equation, we see that right here. So this gets closer and closer to 0 as x gets closer and closer to negative infinity, and it gets closer and closer to 0 as x gets closer to positive infinity. And notice you can actually tell the direction. It approaches 0 from above here and 0 from below here. So for this activity, you're just basically developing the skill of, given two graphs, can you add their y values together to produce a new graph? And then if I give you the equations of the two graphs you used, you then obviously have an equation of the one that you've created by adding, just by combining those two equations. And in the questions I've had you do are these two graphs here. Now you express them as a sum of functions, you have to divide first. So divide using long division. Well, in the first one you use long division. And the second one, you don't need long division, you just divide everything by x squared. So that will break them up into sums of functions. You hopefully know what those functions look like, graph them, and then come up with the shape of f of x by combining the two functions that you get. Okay, that's it for this lesson. Thanks.